So today we're going to start looking at the actual ultrasonic testing, the equipment, test equipment, and what some of those different attributes are, what we're able to control and not control, and then how different features in the part and features in the material, properties of the material, are going to play into the ability to do testing. So just some terms that I'll use throughout the lecture that are important to know. Some of these may sound kind of familiar. You might see some things that look similar to electrical, and they mean similar things in ultrasound that they do in electrical, just dealing with sound now instead of electricity. So the first one there, acoustic impedance, is resistance to the propagation of a sound wave. So, the sound waves do travel through a material, but there's a certain amount of resistance in the material. Okay. The faster a sound wave can travel through a material, the lower the acoustic impedance it has. It also has to deal with what happens to the slower materials have a greater acoustic impedance. Okay. Acoustic interface is the boundary between any two materials of different acoustic impedance. So this can be something like if you're testing a part and it's from one side of the part to the air. It can be from where the test probe sits on the surface of a part. And it can even be within a part. So when you're doing like a composite material, right, you have a matrix structure, you have essentially your epoxy or your resin, and then whatever your fibers are in there that strengthen it. Everywhere it goes from, say, epoxy to fiberglass, to a glass fiber, back to an epoxy, back to glass fiber, each one of those creates an acoustic interface. Okay. Can also be materials that are bonded together if you have multiple layers. One of the Saab 340s I worked on used a bonded metal skin. They had actually 2 or 3 layers of aluminum that made up the skin, of thinner aluminum that were bonded together to create the skin. We would have to do ultrasonic testing after they got damaged to make sure that there wasn't delamination or disbond between those different metallic layers. And then they were also bonded to the ribs and the formers and the stringers instead of being riveted everywhere. And so if they got damaged, we would use ultrasonic testing to look for those disbonds that occurred. Attenuation is the loss or decay of acoustic energy. So this is, impedance is the resistance to propagation. That's how quickly the sound moves, affects how quickly the sound moves. Attenuation affects the excuse me, attenuation affects essentially the volume of the sound, or, the total energy of the sound, right? And so it is, as the material moves through, a material with a higher attenuation is going to reduce the energy quicker over a given distance than a low attenuation material. When we have a test piece and we're bouncing sound off the opposite side, that's known as the back wall, the surface of the test piece opposite where our transducer is. That's used in what's called pulse echo testing. And we primarily we calibrate using what's called our back wall echo, or our back surface echo. Background noise is unwanted signals appearing beside the signal of interest. This can often be reduced by filtering. The nice part is, for the most part, there isn't a lot of extraneous ultrasound in the environment that we're dealing with. Okay, that's why we're using ultrasound. You can use ultrasonic testing, you can perform testing in the same manner in the audible range. The problem is there's a lot of interference out there in the audible range. If we were testing in the audible range that's similar to human voice, everybody's voice that's carrying through the air would cause some kind of an interference with the signal. Whereas ultrasound, typically there's not a lot, some mechanical equipment, vibration, that kind of thing can be on that same ultrasonic level. But when you just have a static piece of material sitting on a bench, for instance, there's really not typically a lot of ultrasonic, that high frequency sound in the general environment. If there are ways to filter it out. Typically, you would pick a frequency that's different from whatever that extraneous sound is, and then you would be able to filter out that extraneous sound. Or it would be a different waveform. Most of our ultrasound is a sine wave. if you have a sawtooth or a square wave or some other kind of random noise wave, you can filter out based on the shape of the wave as well to just look at your perfect sine wave signal. Echoes are where sound reflects off of an acoustic interface. So I put here acoustic interface, and again, I talked about those could be, every time the sound goes from the epoxy to a fiber, that creates an acoustic interface, and that creates echoes. The back wall of the part itself can create is an acoustic interface between the part and the air, and you're going to get an echo off of that. And then the flaw, what we're looking for, any kind of a flaw, right, a crack, it becomes an acoustic interface. And so that's what we're searching for when we do this method. The gain, which is tied to amplitude, is the amount of signal power measured in decibels, and we can look at it in two places. Typically, we adjust our amplifier gain. So how much power we're putting out, what the amplitude of the wave is going into the part. There are some testing methods where you can also, we're sending a signal into a part, and then our test equipment is listening for either the reflection of that sound or for that sound to pass through. There also can be, in some cases, you can adjust the gain of the sensing amplifier. But the equipment we're using, what we're going to be doing, we're going to be adjusting the gain, essentially the amplitude of the signal we're sending into the part. And the louder we send a signal into the part, the higher the amplitude, the further it'll travel. It's less, because that's what, when we look at attenuation is that loss of amplitude. The further it'll travel, but it's more prone to getting interference or to overdriving, getting acoustic interference and clipping in the amplifiers and overdriving the amplifiers and that kind of thing. So we have to keep that in mind. We can turn up the gain to a certain point, but there's a point where we get diminishing returns because of the interference it causes. When we put our equipment on a part, so we're going to have a test material, the material we're testing. And I'll draw just a rectangular block of, say, aluminum. We're going to put our probe against the surface here, and it's going to send out sound waves into the part, okay, from the face of the probe. You will get a bounce, or you will get a echo off of this very front surface here. And that's an initial pulse. That's a non-relevant indication that we'll see on our part. And then we'll also get in a good part like I have here where there's no cracks, this sound will hit this back wall and it'll bounce back up to the top. So that's a back wall echo reflection. So those two are kind of a non-relevant indication. We use them when we're calibrating the equipment to calibrate primarily the speed of sound that we're experiencing on that day. But you will get that initial pulse, and that blocks a certain amount of ability to see directly in front of the probe. Most of these probes rely on a piezoelectric crystal in order to create the ultrasound. So a piezoelectric crystal is it's a semiconductor made up of two materials that when a AC alternating current electrical signal is sent into it, it causes them to vibrate or to move. And so you can translate that AC electrical signal into a matching acoustic signal. If you send in 1 kilohertz sine wave, 1,000 cycles per second sine wave into a piezoelectric cell, you're going to get a 1 kilohertz tone or sound out of that piezoelectric crystal. The flip side to that is a piezoelectric crystal works in the opposite as well. So if a piezoelectric crystal is subject to vibration, it will produce an alternating current sine wave an electric alternating current sine wave in the wires that are hooked up to it. So we can use it to both generate our ultrasound and to sense the ultrasound. It works as both kind of a speaker and a microphone, whether you put power in or not. So it essentially converts mechanical vibration and mechanical pulses to electrical pulses. It can convert electrical pulses to mechanical vibration, which produces ultrasound. You know, sound is just a mechanical vibration, a movement of particles either in the air or in a solid. So we use primarily piezoelectric crystal transducers in order to perform ultrasonic inspection. The method we're going to primarily use is called pulse echo. This is kind of what I've drawn on the board, and this is where we send a pulse of sound into a material, and we listen for a return echo. And we base it on the time, okay? So sound pulse is transmitted, return pulse is received, and we can figure out how far it's traveled by how long it takes to come back to our probe. And so if we get a flaw that is partially through, there we go. You know, as we move this probe over, when it gets to this flaw, you'll get an echo that returns sooner than it would in an area that was unflawed compared to that back wall echo. And so that gives us overall the range we're inspecting. So typically the range, which is the next one, is the distance that we can see on our screen. And we want to see our area of interest. Typically that's from where we put our probe to the back wall of the part. Doesn't necessarily have to be, but typically that's what we're going to do. Okay, we want to be able to see the whole probe. If we make that range too big, we're going to be looking beyond the part. There won't be anything of interest there. In fact, we'll get some extra noise called secondary, tertiary, fourth, fifth, sixth order echoes where this sound keeps bouncing back and forth. And it looks like it's traveled a longer distance, but all it's done is gone back, down and back and down and back and down and back, right? Sound, you saw those when I did the slinky, right? The sound wave didn't just go down and come back to me. If I held it, it could go down and travel back and forth. It can kind of go back and forth in that medium. Through transmission's another type. So pulse echo, you typically use a single probe. You send the sound in. That same probe listens for the echo to come back. A through transmission setup, if I look at my drawing here, would be rather than just a single probe on one side, I'd put two probes on opposite sides. And that way what will happen is now we would have a transmit probe and a receive probe. So we're listening for that echo. So here we have our transmit probe on top. It's going to send this sound through to our receive probe on the bottom. What happens when we get to this flaw right here? What's it going to do? It's going to block a portion, all or some of that sound transmission, right? That's going to hit this flaw and bounce back up. And so there, rather than looking for an echo, we're going to look for a lack of sound transmission. Velocity, we talked about the speed of sound through our material, through our test piece. We have something we have to adjust called our zero offset, and that's part of the calibration procedure. The probe initially, the actual piezoelectric crystal inside the probe is not right at the face. Typically it's somewhere up here, and then what you have is a little bit of a wear surface below that. The piezoelectric crystal itself is too fragile to actually run across the surface of a part. So we have some kind of an acoustically conductive kind of wear material right here in between that actual crystal and the part. So as far as the probe is concerned, zero is right here up at the actual crystal. So our zero offset is we got to calibrate our probe for the fact that the crystal doesn't sit directly against the surface of the part. So we looked at ultrasonic testing frequencies, again, just kind of our audible frequencies compared to where we're looking, the 100 kilohertz to 25 megahertz. Okay. And I talked about what these piezoelectric elements are, so back and forth. So I've got a video that kind of shows it more than just the explanation I provided. Okay, so in ours, the quartz that they talked about in the video there is one, but we also can have lithium sulfate, or probably what's most common for ultrasonic testing is barium titanate. And that's what most of our probes that we have are going to be. They're that barium titanate. So it's a titanium titanium alloy that is used to create a metal crystal in there that can create that voltage and that changing in voltage to create an AC current. Here's a cutaway one of these. I'd kind of drawn it, but this is what I was talking about, where you have here is our actual piezoelectric element. Most of these behind it, you can see this backing material. That's a very dense material. It is a material that has high acoustic impedance, and so the idea behind that is we want that vibration, that ultrasound, to go out the face of the probe, not out the backside of it. And so it helps to direct that. That's that backing material and epoxy potting above it. So epoxy, being plastic, isn't going to conduct the sound as well. And then we have the electrodes, and then I mentioned there's a wear plate on the front because we don't want to be scraping this piezoelectric element directly on the surface of the part that we're testing. In order to get these to operate like they are intended, we need to make sure that the sound is going to transmit into and out of our test piece as efficiently as possible. We don't want to lose any energy. We want to lose as little energy as possible, right? We want that acoustic energy going into our test piece and not experiencing attenuation, not experiencing interference. And so in order to do that, we use a couplant or a material that's designed to couple the transducer. So here's a transducer that is coupled to a piece of material. The other thing it does is you can see, like, this piece of material here was probably a piece of aluminum, has a grain structure to it. It's not a perfectly flat surface. So that couplant fills in any of those tiny, tiny little gaps between the face of the probe and the surface of the material. So it helps to reduce any kind of noise you get off of an irregular, slightly irregular surface. Here they're using a couplant gel, and that's what we're going to be using in class. They are glycerol based. Okay, glycerol is a common ingredient in like hand lotions and that kind of thing. It's basically what like personal lubricants are made out of. So but you can also use a lot of other materials as well. You can use water, you can use oil. There are even air coupled probes where the air itself it's not the best couplant, but it can be used in situations where maybe you don't want to have contact, or you can't have contact and you can't necessarily submerge the part in water or oil, or put a gel on its surface. But the gel tends to be the best, the most efficient of them. It has the least amount of transmission loss, has the least amount of interference. But the drawback is it is a gel. It's somewhat messy. We're using such small amounts that it's not, it really doesn't get all over things. But when you're doing larger tests, or if you're dealing with certain materials, you may not be able to use the glycerol gel. It's fairly non-reactive, but there are potentially some things it could react with as well. When we send our sound into a part, sound doesn't just travel in a straight beam. It spreads out. It actually comes together based on the focal point of the crystal. Oftentimes the crystal is not perfectly flat. It's going to have a focal point where it's going to kind of push those sound waves together. And then past that focal point, from the crystal face to the focus point is called the near field. Past that focal point, then you can see the sound starts to spread out, or it starts to diverge. And we have what's called an angle of divergence there. And that's known as the far field area. Okay? So when we're looking at this, the near field versus far field is going to play a role in what we can detect. So the near field, what you have here is a lot of the waves coming off the crystal are all coming together, are all coming out fairly close together, and actually kind of cross, they kind of make like a crossing pattern. And so you get a fair amount of interference in that area. And so the area directly in front of that crystal there, up the near field area, we cannot really find it. It's not very useful for finding indications. We get a lot of that interference taking place. And so we typically don't say that we can we can accurately find indications in that area. So ultrasonic testing is rarely used for surface directly in front of the surface inspection directly in front of the probe. Now, there are ways to do surface inspection where the probe is not right above the area, where you kind of send the wave along the surface of the part. But you're outside of that near field. The far field is where the waves combine, they form a uniform front, and that's where they kind of spread like I've drawn here. And that's where you get a uniform pattern that is useful for finding flaws. Okay. And the illustration, I've got, again, a video that kind of illustrates this. Let me switch to that. And I'll just go the workaround way to start with. So as was shown in the video, when you have those waves that are kind of coming into each other, that constructive and destructive interference, that's occurring a lot in this near field area. And so your transducer, some of that is going to be picked up by the probe. And so that's why we get a lot of interference there. We can't accurately measure or sense things in that area. Once the waves move past that near field, then they, where you saw those waves kind of hit each other and then they pass through one another and they just continue on their way unchanged. That's what's happening in this far field over here. Now, you will get a certain amount of that interference in the far field from the echoes taking place. But the waves that are moving away from the probe and the waves that are moving back towards the probe, those that they pass through one another, like it shows in the video. And by the time it gets back to the probe, the return wave is a nice clean one, a nice clean vibration that we can sense and that the probe and the test equipment can pick up. So the area immediately in front of the probe is referred to, that near field area is referred to as the dead zone. And so we can't really do any inspection in that area. And part of that too is, in addition to those near field issues, is that we also have the initial pulse bouncing off of the acoustic interface between the probe and the part. Even though we're going to put some kind of a coupling in there to reduce that as much as possible, there's still going to be an acoustic interface there, and it's still going to cause some kind of a reflection of the sound. And so between those, that adds to this near field. So typically the way these probes are designed is that we have our piezoelectric crystal in here, and then we have our wear plate. Ideally, the near field ends somewhere near the surface of the wear plate, so that everything going into our part is past that focal point and is part of the far field. However, it's not always the case. Sometimes that near field focal point, or that focal point, is slightly into the top of the part. So surface flaws, these aren't great for finding surface flaws. The other thing with surface flaws, if we had a vertical surface flaw here, there's not going to be much for it to reflect off of. And so this is, the ultrasounds tend to use more for subsurface flaws. Okay. If we look at the beam, from a little more 3D perspective, you can see it creates kind of a three-dimensional cone. But that energy is spread across the cone. So, closer to the probe, where the cone is smaller, you have the same amount of energy as you have further out, minus, taking the fact that there's a small amount of attenuation and a small amount of acoustic impedance taking place here. But if we had a perfect material that had no impedance, no acoustic attenuation, if you did keep that energy, if you didn't have any loss of energy from the mechanical properties, you would have the same amount of energy at any point. It's just spread over a bigger area. So the energy per a given area does decrease as you move further away from the probe. And then to couple that, we don't have any perfectly acoustic conductive materials, so there's a certain amount of attenuation taking place as well, just from the acoustic impedance that happens. Okay. Another view of that, and talking about the angle of divergence. When they build these probes, they try to make that angle of divergence fairly small. We don't want our probe sending a really wide, typically a really wide sound wave, because we want to be able to know exactly what, if we're finding a crack like this that I have drawn here, if this beam was really wide, would it make that crack appear larger or smaller than what it actually is? As we move our probe across the part, we're looking for it to pick up the crack. So if I had a wide beam, would it make the crack seem bigger or smaller? What? It would make it seem wider than it actually is, because if we had a really wide beam, maybe we'd start to pick the crack up over here. We'd be picking it up, 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 right? Whereas if we can keep our beam fairly narrow, if we can keep that acoustic divergence, angle of divergence, as narrow as possible, we can get a more accurate picture. It also means we're concentrating the energy so we can get a better view directly below our probe as well. We can calculate the near field, how far it is, with this equation. And so the near field distance is based on the diameter of the transducer, the frequency we're using. And so this is why, a given probe, I said they try to set the focal point based on, the probe. But if you use a different frequency, that's going to change where that focal point is. And the velocity of the sound in the test material. Well, one way to do this is they tune probes for a certain frequency. Some of the probes we have are designed, they'll say on the probe that they should be run at 5 megahertz, or they should be run at 10 megahertz. And then they also know what the material is in the wear plate right here. And so if you run the probe at the frequency that is described on it, and with the known wear plate material that's part of the probe, that should create a near field that doesn't extend past the face of the probe. So if you were to run a probe outside of its design frequency, you have a greater potential for causing your near field to extend into the part, right? If I run my probe at a higher frequency or a lower frequency, which one will cause then it's designed, which one will cause my near field or my focal point to move into the part? The diameter of the probe is fixed. The velocity of sound in the test material or in the wear face is fixed. We're not going to change that material, right? So the only thing we can really change in here is the frequency. So when will the focal point move past the face of the probe and into the material? If we drive our probe at too high of a frequency or too low of a frequency? Too high of a frequency. They're directly proportional because the frequency is above the divisor line, right? If we run at a low frequency, it in theory won't go past that face, but we run into some other issues, and that is the lower the frequency, the less sensitive we get. We lose some sensitivity. Okay. The angle of divergence can also be roughly calculated if we know the diameter, the frequency, and the velocity. And so again, this is calibrated. Now this, we can make a difference because now our angle of divergence is primarily looking at the sound traveling in the material. And again, we want to minimize this as much as possible. So the probe, the way it's been designed is to work with a certain frequency, right? So before, we said we could run it at a lower frequency, probably not going to hurt it, but if we run it at a lower frequency, what's going to happen to the angle of divergence here? It's going to cause a larger angle of divergence because it's below the divisor line. Okay? So probes are designed to work with a certain frequency, and you want to set your test equipment to match that. So just an example, typically we're going to be working with aluminum parts. Okay? And we want to know what kind of, how wide of a beam do we end up with in our part. So aluminum, the typical velocity in aluminum is, and I'm doing this in, normally we will be doing our stuff in imperial units, but the calculations go a lot easier for learning in metric because they just play nicer. So in aluminum, the typical velocity is 5,100 meters per second. Okay? And say we have a probe designed to run at 1 megahertz. Now, if you're doing this, you need to remember that that's probably not very easy to see, is it? If you have a probe that's 1 megahertz, that easier to see? Is 1 million hertz, right? So you have to put that, when you're doing this equation, you would have to put that in hertz. It's the frequency in hertz. Okay? Most of our probes are somewhere around anywhere from about a quarter centimeter, or about an eighth of an inch, up to several centimeters, or about an inch in diameter. So say we use a 0.5 centimeter probe. Now this is meters per second, so we got to change that to meters. This is why it's easier to do it this way than trying to convert inches and all that. So that's 5 meters. Okay, 0.005 meters. What's our angle of divergence? How many degrees? This will give you an answer in degrees. So 1.2 degrees on each side, sum total of 2.4. That's a fairly narrow beam, but it's definitely going to have spread. And the further you go away from that face, the further into the part you go, the wider your beam's going to be. So you have to keep that in mind too. If you're looking at we're typically looking at kind of the depth, but if you're doing an inspection that relies on the size, how long, say, is that crack inside the part? Once you get the depth, you got to kind of figure out, okay, if it's really critical to know the width of that flaw or the size of that disc bond, you may have to take into account what the width of the beam is at that point, and would I start picking it up before I'm actually over that flaw because of that angle of divergence. Now, most of the materials we're working with, thin aluminums and fairly small blocks, that's going to be fairly negligible. But there is sometimes where you have to take kind of that, you got to keep that trigonometry in mind and how wide things are in order to know what kind of magnification you might be seeing at a given depth.